So typical dehydration system, we go through a separator, get out some of the oil, gas, and water, hit it with a treater that can apply heat or electricity, and then we go to a stock tank, and we're separating out these three things. But there's, like in this diagram, there's no place for an emulsion to go, because the water's going to go either trucked off or offshore. It's going to go overboard. The oil is going to go down a pipeline, and the gas is going to go to a gas plant. We make emulsions, and we also have solids. Typical Gulf of Mexico configuration, where we've got to start off with a primary two-phase separator, a free water knockout, and a bulk oil treater here. This is where we're doing our water treating, and then we've got some hydrocyclones. Roads, every place needs a trash can. All roads lead to a sump system or a slop tank, and they're normally small. It's offshore facilities. You don't have a lot of room. About this one is, and you can tell with the rule that I just told you, is this is the problem stream. You don't want to be doing this. So the tank shown here is a tank that's going to have solids in it and slop. So you don't want to mix this into where you're trying to separate oil and water and resolve your emulsions. You also don't want to take your clone overflows or your skims from your inert gas flotation cells and recycle them back to the front end. They've already been through the process once, and they didn't end up in the gas, and they didn't end up in the sales oil, and they didn't end up. You don't want them overboard, because then you're sheening. And in any case, if you're deep well injecting it, you don't want it to go there either. So the best place to send them is to a dry oil tank and just move them forward. Designers are going to ask you, 50,000 barrel a day oil facility, or 100,000, and it's treating oil and water and oil. You've got a off spec or within spec oil of 0.5 BS&W. These are your dehy skimmings and your water treating skimmings. Where do you send these two streams? Because they're going to be in high cis. The emulsions will form. What do you do? So what I just showed you, one of the designs takes them and recycles them back to the front end. Another option is you can take them this way and this way, and then is you can send them into the sales system. The question is, where do you think we should tell the designers to send those? Okay, you really want to send them is C. And space within this 87,000 barrels a day within this off-spec oil to send it to the refinery. You're still processing within spec, and you haven't upset your oil dehydration train or your water train. And the main thing you're not doing is you're not mixing fluids that have contacted both dehydration emulsion breakers and water clarifying chemicals. Believe me, we'll show you a demonstration. Why is this happening? Well, the real world's more complex. Most designers want to show that they're not sending any water into the sales system, even though you're allowed to. And the BS&W spec mainly is water. It's not solids. most of the solids offshore end up in the produced water and go overboard. They didn't have a chance to operate, and again, I mentioned the chemical people regard this as proprietary. So you may have two different chemical companies working on the front end and the back end of the system. So you may have Baker working on the fires and someone else handling your water treating chemicals. And I was in Africa one time offshore, and I was bunking with a guy from Baker, and I was talking about this with him, and I said, why don't you guys ever mention this to the operators? And he just kind of smiled, because one of the things is people normally just add more chemicals. So assets spend about $20 million a year on chemicals. Are you overdosing? Are there any interferences? And then how much downtime is being caused by, and loss of revenue by emulsions? Also, how much corrosion is being caused, and we'll show you why that's a problem with the design. So, in emulsions, a normal emulsion, which is a little bit of oil, water and oil, where oil is a continuous phase, and then reverse emulsions, there's in a lot of water. Most reverse emulsions, if not 100% of them, are man-made, where normal emulsions can occur in nature. They look like under a microscope. Normal emulsion, and the right one is a reverse emulsion. You can see physically they look a lot different. One looks like drops located within a continuous phase, and the other one you can see there's some complex interaction with the drops. That's part of the coagulation and flotation and flocculation. Stability is the size. So the smaller the size, the tighter the emulsion, the more difficult it is to resolve into oil and water. In the previous example with the Gulf of Mexico with the slop tank, you remember they showed a centrifugal pump. That's the best pump for making tight emulsions because it just shears the fluid. You really want to have positive displacement pumps, gear pumps, Moino pumps, PCPs. Emulsifiers work is you have a hydrophilic end, which is the dot, hydrophobic end, which is the tail surrounding the water droplets, and the emulsion breakers break this surface tension and then allow the larger droplets to collide and get bigger. And then, according to Stokes' law, the diameter is the most important driving force. It causes the water to drop out of the oil. Reverse emulsions, there's different chemicals. There's surface modification with coagulation, flocculation, chemical to cause them to stick together and then coalesce, which will allow you to skim that off. So, in coagulation, you're using a polymer, and all these are used in parts per million relative to your fluid. So, this is just showing a complex emulsion, and you can see there's emulsions within emulsions within emulsions, and those are even harder to resolve. These aren't going to be separated in your separators very, very easily. These occur is your recycling, and the fix the first time, it's not going to be fixed the second time.